Hello everyone, welcome to Inside Science Center. I am Pushkar Hire and let's talk about vector algebra. So these are the topics that we are going to cover today. Introduction, understanding basic directions, some basic concepts of vectors, types of vectors, vector addition, vector subtraction, sections, formula, dot product, cross product, box product, and then we'll talk about tensors a bit. So if you are a grade 10 or grade 9 student and if you are familiar with basic algebra, trigonometry and geometry, then we are good to go. Let's understand vectors. Introduction. So what are scalars, what are vectors? We have studied, maybe you guys have studied about scalars and vectors in your 9th and 10th standards. That scalar is a quantity which only has magnitude and vector is a quantity which only has both magnitude and direction, and it obeys the law of vector addition, triangle law of vector addition, parallelogram of vector. So these are textbook definitions. So if you want to excel in board exams, then you have to learn these definitions, but let's just understand what they are trying to tell us in a more simpler manner. So scalars are, I've given some examples here. Scalars are distance, mass of object, temperature of object, time at which a certain event happened, and vectors are quantities like displacement, velocity, acceleration and force. So to understand what scalars and vectors really are, we basically need to ask two questions. First question is how much, and another question is where. So if a quantity answers both our questions, it's a vector quantity, and if it answers only one question, which is how much, it is a scalar quantity. Let's understand a bit more. For example, let's take the example of time. So what's the time taken, let's say, to go from, let's say, Nasik to Pune? So one might say, let's say 5 hours. So where is this 5 hours? This doesn't make any sense, right? Where is this 5 hours? 5 hours is 5 hours. Where is 5 hours? That doesn't really answer that question. So time is a scalar quantity. Similarly, temperature. So if a person goes to a doctor and he says, doctor, I have 101 Fahrenheit temperature, the doctor won't ask him where is this temperature, right? It won't make any sense. So temperature is also a scalar quantity. So what really are vectors? If it answers both of the questions, how much and where, it is a vector quantity. If it answers only how much, then that is a scalar quantity. For example, force. If I were to, let's say, push a table, correct? So I am applying some force in that direction, right? So it answers where are you applying force, and I can tell I am applying that force in that direction. So it gives a sense of directions. So it is a vector quantity. Okay. Talking more about distance and displacement, what exactly is distance? What exactly is displacement? Let's understand what is distance. Let us understand what is displacement. So let's say this is my house, and let's say this is my friend's house. So the path from my house to my friend's house is not a direct path. It's not like I have a jetpack and I can directly go from point A to point B, correct? The path is quite, I have to go straight, then I have to take a left turn, then a right turn, then a left turn, then right turn, then go around a park, and then I can go to his house, right? So this is what is displacement. This is the actual path. So this actual path is nothing but the distance. And this shortest path, let's say if I had a jetpack and I can directly travel from A to B directly by flying. Shortest path, the shortest path is nothing but displacement. We'll talk more about distance and displacement when we study more about, let's say, kinematics. But now let's understand what vectors are. So I think this just gives you a basic understanding of what scalars and what vectors really are. So why are we studying this? Where do we use vectors? So we use vectors almost everywhere in physics. So this is a picture of a robot from Boston Dynamics. So how do we use vectors here? Like how do we? What's the relation between robotics and vectors? So we can see that all these, let's say the leg bone of that robot, all these things are called as links, and these points are called as joints. So by how much do we rotate these joints and where exactly this link will go is essentially all vectors, isn't it? How much and where. So this is how we use vectors in robotics. I am giving it in a very condensed manner. It's quite complex than what it actually is. But let me not scare you. Let's just understand what vectors is all about first. And this is quantum mechanics. So you guys must have heard about what quantum mechanics is. So in quantum mechanics, these electrons and all these subatomic particles do lots of crazy stuff, and where exactly are there? Maybe you guys will study more about Heisenberg's uncertainty and what exactly do they do. It's all very complex, and it's all usually given in a vector space, all about its positions, all about its wave nature. It can all be explained by vectors. And this is an launch vehicle. This is PSLV launch vehicle, and here also we use vectors. We see where exactly do we in which altitude, in what direction do we send this launch vehicle. It's all about vectors. So these are some interesting applications of vectors. So this is why we should study more about vectors. Okay. For example, let's talk about launch vehicles. So in a launch vehicle, there is this exhaust from where all these gases come out, and this exhaust is called as a gimbal because it kind of jingles year and year, and depending on how much and where does it exactly point to, the direction of the rocket's trajectory is all dependent. So this is how vectors is kind of used in launch vehicle mechanics. And let's say if this is India and let's say this is Sri Lanka, so this is somewhere is Sriharikota, which is the launch site of Indian launch vehicles, and it has to launch in a certain direction such that it goes in this direction, launch vehicle. So this is some basic what vectors is all about. You guys must have been seeing that I am drawing lots and lots of arrows here and there. So essentially we'll understand this right now. It's all vectors. So let's understand directions. So you guys all have all heard about the cardinal directions, which are nothing but the north, south and east and west directions. But is it not correct that Japan, which is let's say somewhere around here, and let's say India can also be on the west of United States, right? Or no, is it not like that? So actually it's not like that. Why? Because in order to understand what east, west, north, south is, there has to be a reference point. And which is that reference point, if you ask? That reference point is because of this longitude, which is called as Greenwich Meridian Time. So I'll just write a little g, and this latitude, which is nothing but our equator. And this is our reference point from which all these directions have been laid out. So everything to this side is east, is essentially United States is a western country, correct? So this is west because this is India, correct? So it's in that direction. So it's a western country. Okay. Japan is not a western country for United States. Japan is an eastern country because this is the reference point. Are you getting what I'm trying to say? Okay, if it's not clear, we'll just understand it in a more detailed manner. So what I'm trying to say basically is east, west, north, south. These are our cardinal directions. But the point is east, west, north, south are not sufficient to tell directions of lots of things. It's sufficient for our terrestrial navigation, but if we go out a bit, we cannot tell that, let's say, Saturn is in the east direction. This is not east direction, because east, west, north, south is all on Earth. Once we go out of Earth, it's not east anymore. Similarly, Jupiter is not on the west side of Sun. Okay, so as we can see, there is some problem with this east, west, north, south directions. And how do we solve this problem? How do we generalize this problem? We'll understand it in these basic concepts. So first of all, what is a vector? So vector is generally represented by an arrow. This point is its initial point. So I'll write it I here. This point is its final point, so I'll write an F here. This length is its magnitude. And this arrow represents its direction. So this is how we usually draw a vector. So understanding what basis vectors is, basically we live in a 3D world. So you guys are familiar with what dimensions are. Units and dimensions, it's the first chapter in physics. So there are 3 dimensions of length in this world. And these dimensions of length are independent of each other. What that means is, usually these 3 directions should just be perpendicular with each other. You guys can try, you can only draw 3 mutually perpendicular vectors and not more than 3, because we live in a 3-dimensional world. There are some concepts about 4-dimensional worlds, 5, 6 and so on, but it's all an imaginary concept. We cannot physically see, there's no such thing as seeing a 4-dimensional world, because we are all accustomed to a 3-dimensional world only. So there are only 3 possible mutually perpendicular vectors, and these 3 directions can be generalized as I cap, J cap and K cap. And how exactly we assign I cap, j cap, k cap like this? We use a rule called as right hand thumb rule. We'll study about right hand thumb rule later on. But what exactly is the I cap, j cap, k cap? Well, I cap, j cap, k cap can be anything. So to solve our problem from our topic earlier, is I cap, j cap, k cap can be anything. So in this context, I cap can nothing be be east, j cap can be north, and k cap is this up direction, which is outwards. Or I cap, j cap, k cap cannot be east, north, and up. It can be a different direction altogether, depending on what context it is. So I cap, j cap, k cap in a celestial plane can be these directions. So we can say Jupiter, Saturn is on the I cap kind of direction from Sun, and I don't know, is this Uranus, Neptune, whatever. So this is this Uranus, Neptune is kind of in the k cap direction from the Sun. So what direction is Jupiter in? What direction is this America in? So America, being a western country, west is opposite of east, and opposite in a number line. If I draw a number line, this is 0. In the right hand side of 0, we have all positive integers and positive real numbers. On the left hand side of 0, what do we have? We have negative, right? So west can be represented by minus I cap direction. So this is minus I cap, this is I cap, this is j cap. So south can nothing be, south can be nothing but minus j cap direction. And if this direction is up, this direction is, let's say, k cap, so down can be minus k cap. So this is all 3D. It's hard to explain it in a 2D screen. You are looking this video in a screen. It's hard to explain it in a screen, but it's quite easy to understand when we think about it. Correct? So I cap, j cap, k cap solves our problem about a reference coordinate reference frames and reference directions. So I cap, j cap, k cap can be east, north, up. If you are familiar with east, north, up, you can just say E cap, N cap, maybe U cap instead of I cap, j cap, k cap. However, if it feels comfortable. But you cannot use east, west, north, south in a celestial plane. That's why it's better to use I cap, j cap, k cap. Okay. Let's talk about pick and place. So what is this pick and place? So essentially, like I said earlier, if India is, let's say, in this direction, Japan is also on the east kind of direction, correct? From India. South Korea is also on the east direction of India, correct? So this vector is also east vector, this vector is also east vector. So we are essentially just picking and placing that vectors. We are not rotating those vectors, and it's okay. So this is a general rule that you can pick and place vectors, but you cannot rotate those vectors, correct? Let's see in this direction. So this direction is west, and which direction is this? This is also a west direction, correct? If this is east, this is also east, this is also east, this is also east. So I'm picking this vector and placing it, right? I can pick and place this vector. Wait a minute, let me just pick and place. Correct. So I can pick and place this vectors. Until unless I don't rotate it or don't place it in another plane, it's okay to pick and place vectors. So let's understand what scalar vector multiplication is all about. So scalar vector multiplication says, so if this direction is a small, let's say I cap direction, if I take one more I cap direction here, this will be 2 I cap, correct? If I take one more, there are 3 I caps, so it is 3 I cap. This is 4 I cap, correct? So essentially what we are doing is we are multiplying this vector with this scalar number 4. So 4 I cap is nothing but the scalar vector multiplication. So if this direction is j cap, if I take 4 more j caps, so this thing becomes 4j cap. What happens if I do 4 times 4j cap? I'll get 8j cap, correct? No, I won't, because 4 4s is 16. So I'll get 16j cap. Okay. So this is how you multiply a scalar with vector. You simply multiply it, you just don't think twice. Okay. I think maybe you should think twice before multiplying, but it's okay. So let's talk about the 2 ways of representing a vector. The 2 ways of representing a vector are magnitude and angles and components. So what are magnitude angles? What are components? Let's study about it. So let's say we are in this room, and let's say that there is a fly sitting over here. Okay. So if you guys want to call it east, it's okay, you can call it east. If you're not too comfortable with I cap, j cap, k cap, it's okay. So let me call this east direction, let me call it e cap. Let's say this is an up direction, let me call it u cap. So where is this fly sitting? So I think I have to go 1 east, well, let's say 1 meter east, then let's say maybe I have to go 2 meter east, and maybe let's say 2.5 meter east. So I have to go 2.5, 2.5 meters, let's say east, e cap, and then I have to go, let's say 1 meter north, and then let's say 0.5 meter north. So maybe I have to go not north, up. So I have to go, let's say 1.5 u cap. So from basic Pythagoras theorem, I can calculate how much this length is, and how much is that length? Let me just calculate it. It's, let's say this is r, from this point to this edge of this room to that fly. So r square is nothing but 2.5 square plus 1.5 squared, correct? So r square is nothing but 6.25 plus 2.25. So I'll get 8.5. So r is nothing but root 8.5, correct? So let's say it's approximately 3 meters approx. So basically what we have done is r represents the magnitude 3 meters in an angle, let's say this angle is theta. So either I can say that that fly is at an angle theta and 3 meters away from this reference point origin. Magnitude angle form can be written as 3 meter in theta direction, or theta angle. This is the magnitude angle form. Or I can say in component forms that either you go 2.5 meters in E cap in east, and you go in 1.5 meters in the u cap direction, in the up direction. So this is the component form and this is the magnitude angle form, and we just saw the simple example where to find this 3 meter, what we essentially did is we used the Pythagoras theorem to square the components and add it up and take the root to find the r vector. And to find the angle theta, maybe we can use a basic trigonometry. We can use, let's say, tan theta. Tan theta is nothing but the perpendicular divided by its base. So it's nothing but 1.5 by 2.5. So essentially it is 3 by 5. So tan theta is 3 by 5. So this is how we find the trigonometric ratio, and once we understand what trigonometric ratio it is, we can easily find out what theta is. Okay. So let me just recap what we did here. When we are talking about 2D objects, we are talking about two-dimensional objects, space. In a 2D space, if I have components, I have, let's say, xi cap plus yj cap. If I have these components, I can convert these components to magnitude r and angle theta by simply using Pythagoras first. R is nothing but root of x square plus y square. And how can I find that theta? We can use a simple trigonometric ratio. It's not just that I can use tan, I can use any trigonometric ratio. I can use sine theta, cos theta, tan theta, sec theta, any trigonometric ratio is okay. So tan theta is nothing but y by x, and I can convert it like that. How do we go the other way around? What if I have r and I have theta? Then how do I go from r and theta to find out what components do I have? So it's easy. I can simply use basic trigonometry. So if this is theta, this is x, this is y, and this is r. So I know, if I know r and if I know theta, what I can do is I can use, let's say, sine theta. Sine theta is nothing but, okay, sorry, I'm sorry, this is x should be on the base. Okay, so let's say this is y, this is x. Sine theta is nothing but perpendicular upon base. No, it's not perpendicular on base, perpendicular upon hypotenuse, or y upon r. So I can find y is nothing but r sine theta, correct? It's in the division, it will go in multiply. So y is r sine theta, and what is x? Similarly, I can use cos theta, cosine theta. So cosine theta is nothing but x by r. So I can say x is nothing but r cos theta. So to get magnitude angle from components, we use Pythagoras theorem, and to get components from magnitude angle, we use basic trigonometry. Okay. Okay, so moving on, let's say that fly flew away, and now that fly is sitting on this edge of this window, this corner of that window. So now what happened essentially is to get to this fly, let's say this is I cap direction, let's say this is J cap direction, let's say this is K cap direction. Okay, to get to this fly we can go a lot of ways, right? So we can either go some x distance here, xi cap, then we can go a few distances in the j cap, let's say yj cap, but even after going there I need to still travel in the k cap sort of direction, zk cap, to reach that fly. Or maybe I can go in y cap direction first, and it actually doesn't matter. So I can either go in j cap direction first, so this is yj cap, then I can probably go zk cap later on, and then I can go in the x direction to get where this fly is. Correct. So essentially, even if I change the order, the components are still the same. Components are still xi cap plus yj cap plus zk cap. It doesn't really matter what order you write. It has to be x, y and z. Then only you can reach that fly from that corner. So these are the components. And to find magnitude, what can we do? Let's talk about what can we do in a minute. But let's understand the fundamental difference between 3D angles and 2D angles. So in 2D angles, it was sufficient that we only defined one angle theta, because other angle would naturally be 90 minus theta. Correct? But in 3D, the problem is that one angle is not sufficient. We need to see angles from all three axes. So we need to see this angle. Let's say I can say theta x. I need to see theta y also. And I need to see theta z also. And obviously theta x, theta y and theta z, their summation is not 90. It can be anything. It's quite obvious to see in this diagram that theta z itself is an obtuse angle. Okay, so it's not so easy in 3D to find these theta x, theta y, theta z. So what do we do? So we use a certain terms called as direction cosines. So what are these direction cosines? Let's talk about it in a bit details right now. So first let's talk about converting xyz. Let's say if I have xi cap plus yj cap, and let's say if I have zk cap to r. How do I convert these components to magnitude? So to convert these components to magnitude, what I can do is simply in this diagram, it's a bit obvious. If it's not, let me just copy and paste this diagram and understand what exactly is happening. So in this diagram, that fly is sitting over here. What I'll do is let's say I go certain direction here. Let's say this is y. Sorry, this was not y. This was, let's say, zk cap. So I went in this direction first, zk cap direction. Then I went in this direction, which is nothing but our x direction. So this is xi cap direction. Okay. So after that, I went in the y direction. So this is yj cap direction. So basically, I have formed a right angle triangle on the floor here, and let's say if it's a 2D right angle triangle, so I can find what R1 is first, and R1 is nothing but R1 squared is nothing but x squared plus z square, correct? From Pythagoras theorem. And after we reach this point, it also forms another right angle triangle from the origin to this point, which is this right angle triangle. And the base is R1 and the perpendicular is yj cap. And this is what we want R. So how do we find R? We use Pythagoras theorem again. So R squared is nothing but R1 squared plus y squared. Okay. So simply I can substitute R1 squared as x squared plus z squared, and I get R squared is nothing but x squared plus z squared plus y squared, correct? And essentially I get a 3D Pythagoras theorem. I get what R is nothing but under root of x squared plus y squared plus z squared. So this is how you find out the magnitude from the components from 3D Pythagoras theorem. Okay. And how do we find out the components from magnitude? So if I have magnitude and if I have angles, how do I find out components in 3D? So if I have, let's say, R, and if I have theta x, theta y, and theta z, if I have all these things, how do I find the components? Basically, what we do is we simply take, let's say this is R and this is x I cap, correct? This angle will be theta x. Similarly, the other angle will be theta y if the base is y, and similarly the other angle will be theta z if the base is z. It's difficult to draw it in a 2D screen, but it's easy if you just imagine it in your 3D world. It's quite easier. And similarly, since as we did it in our 2D, we simply say x upon R is nothing but cos theta x. So I can say theta x, I can say x is equal to R cos theta x. Similarly, we do it with y. Y will be R cos theta y, and similarly z will be R cos theta z. And essentially we got all these cos theta x, theta y and theta z. These are nothing but the direction cosines. Okay, let's talk about types of vectors. So there are lots and lots of types of vectors. So I've just compiled the basic types of vectors. First one is zero vector. So as the name suggests, zero vector is a vector whose initial and final points are the same. So it has no length, it has no magnitude. So we can say it has no magnitude, but it has infinite directions. So if it doesn't have any magnitude, it's essentially pointing at all directions at the same time. So that is what a zero vector is. What is a unit vector? Unit vector A is a vector whose magnitude is 1. Okay, and we use the unit vector is denoted by a cap. So when we are talking about I cap, j cap, k cap, so I cap, j cap, k cap were essentially the unit vectors in this direction. I cap direction, j cap direction, k cap directions. So unit vectors are good to represent directions of a vector because their magnitude is 1. 1 can be any unit. It can be centimeter, 1 centimeter I cap, 1 meter I cap, 1 kilometer I cap, whatever. But these are what unit vectors are. Its magnitude is 1. So in the before section, when I said x is r cos theta, y is r sin theta, and before that when I talked about 2D, where y was r sin theta and x was r cos theta, I can say that r vector is nothing but x vector I cap plus y vector j cap. Let's say I'm talking about a 2D thing. So if I divide this vector with, okay, its magnitude is obviously magnitude of vector was root of x squared plus y squared, correct? So is this a unit vector? It is not a unit vector if x squared plus y squared is not 1. And it becomes a unit vector if x squared plus y squared is 1, isn't it? So what happens if I divide this vector with its magnitude? I get r vector as x I cap upon root x squared plus y squared. I'm dividing it by its magnitude plus yj cap upon root x squared plus y squared. Okay. So you can see that this is nothing but base upon hypotenuse. X by root x squared plus y squared is nothing but base by hypotenuse. So it is, what is it? It's cosine theta, right? So it becomes cos I cap. And y by root y squared plus z squared was cos theta I cap. And what was this? This was sin theta j cap. Correct. So now this becomes a unit vector because sin squared theta plus cos squared theta is 1. Okay. So unit vector u cap is nothing but vector divided by its magnitude. So I can write down a simple formula. Any vector, let's say a cap, is nothing but that vector a upon its magnitude of that vector. Okay. So let me just erase this because this is r cap. Okay. I hope I'm not going too fast, or am I going too fast? Maybe you can write it down in the comment section. So what are co-initial vectors? Two or more vectors having same initial point are co-initial vectors, right? So when I was talking about the Greenwich meridian and equator, the point from where all these vectors were originating, which were nothing but the east, north, south, west, all these directions, these all directions were co-initial directions. These all vectors were co-initial vectors because it were originating from any point. If you're taking a compass in your hand, you're getting all those vectors from the same point, right? So all those vectors are co-initial vectors. So what are collinear vectors? Two or more vectors are said to be collinear if they are parallel to the same line irrespective of their magnitudes and directions. So if I have a vector these two vectors are collinear. Why are they collinear? Because they are parallel, right? This is also in the east direction, this is also e cap, and this is also e cap, so they are collinear vectors. Obviously their magnitudes can be different. This can be, let's say, 2 meters east, this can be 1 meter east, but essentially they are still going the same direction, so they are co-linear vectors. One important point to notice is that their units should be the same. So if this is 2 meter, this has to be 1 meter. Okay, instead of saying units, I would rather say their dimensions should be same. I cannot say 2 meter east and then 1 Newton east. Okay, it's also collinear, but yeah, essentially their directions should be same. Let's talk about equal vectors. So this is where my point of units being the same comes in. That if the two vectors are said to be equal, if they have the same magnitude, unit and direction. So if I have 2 meter east and I have 2 centimeter east, they are not equal because the units are different. Okay, so they should have the same magnitude, direction and unit, then these two vectors are equal. So if I say this is A vector, this is B vector, and this is C vector, then I can say A is equal to C, but it is not equal to B. Okay. Negative vectors. So what are negative vectors? A vector whose magnitude is same as that of a given vector, but its direction is opposite, is nothing but, so essentially east and west are negative vectors of each other. North and south are negative vectors of each other. So I cap, it becomes minus I cap. If I have j cap, it becomes minus j cap. So I think let's stop our lecture here today. I have lots and lots more to cover, but I think maybe I am going a bit too fast. Maybe you guys can let me know in the comment section. So thank you for today's lecture. See you in the next one.